I think you're a good number to start. I see you are 9 of us in the call. The rest can join us as we continue. So I'll start by introducing myself and the session, then I'll hand over to Nick, then he'll take us through the rest of the session. So Collins Negoti, and I'm the lead of MLSA Dekut. MLSA is Microsoft Learn Student Ambassador. That's a program by Microsoft for students who are passionate about tech. And we usually host this session, IoT 101 series, where we cover everything IoT and embedded systems. And tonight, we are privileged to have Nixon Kiprotich. Nixon is a good friend of mine, a friend, a partner, a cosmate. We do a lot of things with Nick, and we're privileged to have him here today for our session today. And we'll be looking at making IoT devices more efficient and smarter with FreeRTOS. So Nick, I hand it over to you because you're the man of the hour. And also tell your friends to join. This is a session you don't want to miss. As the people are here, I said, Nick, please. Hello. Nick, you can take over. Okay.
Oh, so hello. So before we start, I think I can confirm if you guys can confirm if you can hear me clearly. Is the audio okay?
Yeah, loud and clear. We can hear you loud and clear.
Okay. Thank you. So I think we'll begin right now. So I think I can introduce the session first before I introduce myself. So the session today will be taking your IoT projects to the next level with FreeRTOS. So the main goal of the session is how can you make your projects more sustainable? Like normally when you're building your IoT projects, you normally develop maybe for just development purposes. But have you ever considered like what happens when you have now built a project that is deployed somewhere and it's supposed to work for 10 years? So how is that device supposed to work out there for 10 years? So if you've been working on projects, you realize that you sometimes build your maybe a simple IoT project, then at the time of presentation, you notice nothing is working. Yet at the time of coding or the time you are building the project, everything was working clearly. So I think we look into some of such stuff as we continue. So let me introduce myself. So can see me smiling there. That's that's a selfie I took some while back. Okay, but that's not relevant now. So I'm Nixon Kiprotich. I'm currently a fifth year mechatronics student at the Dan Kimathi University of Technology. Apart from that, I am an IoT, TinyML, and robotics developer. So if you know me, you've seen like the kind of projects I do measure mostly in IoT, robotics, and sometimes TinyML. So I'm also an open source projects contributor. I contribute a lot in open source projects, also especially in IoT and TinyML and also in robotics. So you can find me in LinkedIn. It's just Nixon Kiprotich, also at X, Hackstar.io, GitHub, and I also have account in other platforms, but I'll be able to share that later on. So some of the projects I've worked on is TN24. So I'll also share more about some of the projects I've worked on, but these are my favorites. Probably you've seen some of them. So I think we can begin the session, then I'll be telling you more about myself and more about the projects I've worked on. So before we introduce what FreeRTOS is, I think it's more convenient we first know why is it necessary. So yeah, I'll begin here. So the traditional approach to the systems project or an IoT project, most people begin with Arduino, and the way Arduino IDE structures the code, you normally have the void setup and the void loop. So what normally happens is you define your parameters here. Maybe you initialize let me say initialization. You initialize your sensors, maybe you initialize your serial monitor. Then as the loop is where you run most of your tasks. So what is a super loop? So the way the code normally runs is you say, like, for example, I'll be using this example most of the time throughout the session. So let me talk about it a bit. So let's say we have a DHT11 sensor and let's say what other sensor? Let's say we have a DHT11 sensor, we have an LDR sensor, and let's say we have some actuators like an LED or maybe a fan. Yeah. So what happens is maybe the first task you say, you read the temperature and DHT from the sensor. The next task you maybe read, what was the other sensor? Okay, let's say like an LDR, you read the light from the LDR, then maybe task 3 is when you maybe actuate the fan or maybe the LED depending on the temperature or the light. So there are challenges with this. For example, we will first have to read the first sensor, then we go to the second sensor. Let's say at the time of reading the first sensor, something happens that the second sensor was supposed to detect. So you'll see in our code, we will not be able to detect that challenge because we are using delay. Because most of the times we use delay in this format. Let's say I'll give you another example during the demo part where you can also try it. Let's say the first task is to read the temperature and humidity from the DHT11 sensor. The next task is to maybe sense the light. Then the third task is to blink an LED or maybe run the fan. So I'll give an example. Maybe you're using this LDR to detect someone passing maybe through a door. So let's say during task 1, when we are reading the temperature and humidity, somebody passes through the door. So the sensor is not able to detect that because we were delaying on the first. So then again, we go to the task 3. Let's say we say let's turn on the fan. So as we are turning on the fan, something happens and the DHT sensor was supposed to detect it. So we are not able to detect it because the microcontroller is focused on the third task. So some of the limitations of using this is like blocking delays. Let's say you run a delay, for example, 10 seconds. You're turning on the light for 10 seconds. So as this is happening, the microcontroller is focused on that task and it's not able to execute other tasks. So yeah, we also face poor scalability. You cannot scale this project to maybe you are working on a complex device, so where everything is supposed to happen simultaneously. Let's say you have okay, let me use an example, your smartphone. Your smartphone is supposed to be connected to the internet at the same time you are typing, at the same time you are playing music. So let's say you are given a task to program the mobile phone. Using this format of Superloop would not work because the tasks are happening simultaneously, and as you can see in these things has to happen in order. So yeah, we cannot use this. So that's where now FreeRTOS comes in. So what is FreeRTOS? FreeRTOS is an open source real-time operating system. It was developed by real-time engineers, but it was later sold to Amazon. Okay, is it really sold? Okay, let me not use the word sold, but AWS is the one that maintains it and uses it in their IoT devices. So the advantage of FreeRTOS, it's lightweight and scalable, and it's also open, so anybody can be able to contribute in it. There are other FreeRTOS like Zephyr, other RTOS, other real-time operating systems like the Zephyr RTOS and some of the others. I'll show you some of them. But FreeRTOS is the lightweight one. You can be able to deploy it in microcontrollers and other boards. You can also be able to do that with Zephyr, but it's more complicated compared to FreeRTOS. So I'd say FreeRTOS is a beginner-friendly real-time operating system that you can get started with it. So this is how a FreeRTOS works. You can be able to have tasks and you can be able to manage your resources. So I'll show you how this works later on. So I think we can continue. One thing before we continue, I think I can talk about this. So the difference between FreeRTOS and other operating systems like maybe Linux, Windows, or maybe the Mac OS. FreeRTOS is specifically designed for microcontrollers, or I'd say lightweight applications. So its application is more specific. You see OS like Linux or Windows, they are meant to be used in many purposes. You can have video players in it, you can have browsers, you can have many other applications. But with these real-time operating systems, they're specifically made for a specific purpose. So let's continue. So how I'd like to talk more about tasks. So you see in the previous one, we had tasks, but they were running concurrent, no, not concurrently, like they had to run in order. Like the first task has to happen, then the second one, then the third one. But you see in FreeRTOS, all the three tasks can run simultaneously. Let's say, for example, task A could be reading the data from the DHT sensor. Task B could be reading the temperature, or not temperature, reading the light from the LDR. Then task C could be actuation. So, for example, in your mobile phone, let's say this could be handling, maybe you are typing, you are chatting with somebody on WhatsApp. Then this is handling maybe you are playing music with Spotify. Then this could be handling some other task. But let's go back to the other one so that you see the difference. So you see in this one, the tasks were running one by one. This one has to happen, then this. So imagine if this was happening in your mobile phone, like you have to text your friend first, then when you're done with that, you go back to listening to your music, and then maybe go back to doing something else. This could be tiresome and you could not be having the same experience with your mobile phone. So yeah, let's continue. So in a anatomy of a task of a FreeRTOS. So you have to define some parameters in your task. So you'll have the function, then you'll have the stack size. So the advantage of FreeRTOS is you can assign specific memory size. You can allocate some specific memory size to your task. Let's say the task for blinking an LED. You see, that's a simple task. You can assign a bit of less memory. But when you go to a task like displaying something on a TFT display, you can assign more memory because that's a more complicated task. Then you can also have priorities. For example, you are building an IoT device that's supposed to be doing some sensing and all. So you can give priority to some sensors, like which example should I use? Let's say a fire alarm. So you can give more priority to the part that detects smokes or detect fires. So that could have more priority compared to other tasks that are maybe not more important. So that's a good thing with FreeRTOS. You can define the other tasks. You can give other tasks a priority. I'll give another example. Yeah, a device that does sensing. So you can say like the moment you initialize the device or you restart a device, this task can run fast, like maybe initializing your sensors before you do other tasks. Then we have other parameters. I'll show you how it looks like as we continue. So let's continue. So we also have states in FreeRTOS. You can have a running state, a ready state, and a blocked state. So we also have transition. So tasks, or not tasks, I mean states and transitions are almost similar, but state is what's happening, then the transition is what's happening, like from maybe one task to the other one. So in states, we have a running state. So maybe that's collecting data. So we can be actively collecting our data. Then ready state is like it's ready to run. For example, we can have a task to maybe push our data to the cloud. So we could have like when the sensor is collecting data, the task to push the data to the cloud could be ready. So after collecting the data, we push the data to the cloud. And then block task could be maybe you're waiting for a delay or for an event to happen. So, sorry. Let's say, for example, actuation. We can say we block this actuation. It cannot happen until when maybe the sensor detects movement is when we can turn on the lights, something like that. Then suspended is a task that is not eligible to run. Then you have transition. So it's just the same, like the explanation is almost the same as I had explained with the states. So you can look at this table. I'll share the slides later on. You can learn more. I'll be going quickly because I also have to show you some demos. So we also have task scheduling and priorities. So I talked about priorities, like you give a certain task a higher priority so that maybe it runs immediately. You restart the device or immediately something happens. So yeah, let's continue. So here are some of the essentials of FreeRTOS. Like these are something that you should be conversant with if you'd like to use FreeRTOS. So I think you can read from your side. I don't have to explain everything, but I think I did not include tasks in this, but you should be able to know about it. So you should know about tasks, timers, okay, we use timers, not delays in this part. I'll show you how that works. So let's go to demo one. I think you'll understand more as as we do the demo. So I'll go to this link. So can you see this screen? Collins, can you confirm if you can see the simulation?
Yeah, we can see. I can see yeah, we can see it.
Okay, cool. So this is the first demo. I'll show you what happens in the super loop way. So we have here in the void setup, we have defined our pin. So we have D2, D3, and D4. So let me try to zoom in a bit so that you guys can see it more clearly. Yeah. So we have attached the LED, the red LED to D2, then the green to D3, and the blue one to D4. And then here we have the task. So you see, what will be happening here is we'll blink the first LED, and then the second one, then the third one. So everything will run in order. So let me run the simulation. Yeah, you can see what's happening. It's blinking one by one. So I'll ask you a question. What would you do if you wanted to blink the three LEDs at the same time, but with different rates? Like maybe you wanted this to blink maybe 3 times every second, this to blink 2 times every second, and this to blink 1 time every second. How would you do that? So you see, with this setup, you cannot do that because we have to wait for this to happen, and then for this to happen, and then this. So let's say maybe I reduce the delay for this to maybe 100 milliseconds, then maybe increase this to 1 second. So let's run the simulation. It's taking a bit of time to be patient. Yeah,
Nick,
but
as you wait, there was a
as I
hand that was
was
up.
explaining, so somebody happy. That was that?
As we wait for it to compile, there was a hand that was up. So I don't know if it's a question. I don't know if I don't remember. Mark, you had your hand up, so you can unmute and speak out.
Nixon, kidogo ulikuwa na breaks. Sijasikia kitu for the past 3 minutes. Ama is it from my side ama ni kila mtu? Hello, unanisikia?
So yeah, nakusikia. So Collins, could you confirm if it was the error on my side or it's just Mark's side?
Okay, you are breaking a little, but on my end, I could hear you a bit. But maybe on his end, you can just repeat maybe the last like 3 minutes of what you are saying.
Oh, okay. Sorry about that. You should. Okay, next time you can maybe unmute and speak because I was looking at the slide, so I did not know if you
Okay, sawa.
addressed you. So okay, I'll repeat as about that. Let me go back to the slides. So which part was I breaking? Which part specifically?
The part where you're explaining about state and state and the other one was what? State and is it running?
Okay, let me go back to that. Oh, here, when I was explaining about states and transitions.
Hapo sasa.
Oh, okay. So what I was trying to say here is, okay, state is what's currently happening or the task that's going on at a given time. Then the transition is what's happening between one task to another. So in the states, there's a task could be actively running, it could be ready. So for ready, it could be ready to run or waiting for CPU time. Then there's a blocked state. For a blocked state, it's not currently running, but it's waiting for something. And then for a suspended state is a state, like is a task that's not eligible to run. So for example, a running state is we can be having the microcontroller actively collecting data from a given sensor. But then with a ready state, we could say that the microcontroller has collected the sensor, but we need to push it to the cloud. So maybe the task to send the data to the cloud is ready to run. So it's not currently running, but it's ready to run. So once you've collected the data, we can send it to the cloud or to a server. Then a blocked one is maybe somebody trying to speak. Okay, let's continue. So I think you've understood that. So the transition is what's happening between one task and the other. So a ready transition is just like a running state. So let me go back to the demo. It's this one. Yeah, so you can be able to see in this super loop format that the LEDs are blinking one after the other. You cannot be able to blink them simultaneously. So I'll show you another example where we can be able to blink them simultaneously, or maybe we can do different rates with different LEDs. So let's go to the next demo. This one. Yeah, this one here. So this one is a FreeRTOS example. So in order to use FreeRTOS in your code, you have to include it. So you include FreeRTOS, then you include FreeRTOS tasks. Like I was telling you, there are tasks in FreeRTOS, so you have to add them. Then we define our LED pins. So we would attach the red LED to D0 and the green LED to D1. And then since we'll be having two tasks, the first task is to blink LED1, then the other task is to blink LED2. So we also have to initialize the tasks here. So here we have task 1. So we'll be blinking LED1 at 500 milliseconds rate. Then we have task 2. So for task 2, we'll be blinking the second LED after every second. So yeah, that's okay. So you'll be able to see that both LEDs will be running concurrently. Like as this one is blinking at its own rate, the other one is also blinking at its own rate. It doesn't have to wait for this, and then the second one blinks. So let me zoom out a bit. So here is where we create our task. So the first task is blink LED1, and then you have to give it a name. And then here is the memory size we are allocating to that specific task. Then yeah, we are giving it priority 1. So
Pardon, Nick.
this
Pardon,
task.
Nick.
So I
Nick,
I
pardon.
repeat or
I'm not seeing the walkway screen. I'm seeing the slide. Nick, can you hear me?
yes, I can hear you.
I'm not sure which screen you're on right now, because the screen I'm seeing is the demo slide, but the way you're talking is like you're on the walkway screen. So I'm not sure if everyone is facing the same issue.
So
Yeah, perfect.
are
Now
you?
it's perfect.
Oh, were you able to see the previous one with the 3 LEDs? Or you are facing the same
Yeah, the
challenge?
first one we saw it, but yeah, now we can see it. Now you can continue.
Okay, no problem. So I guess I'll have to repeat. So at the beginning of the code, you see we have to include the FreeRTOS. So for you to use FreeRTOS in your code, you have to first include it. Then we also have to include the task because we'll be using the FreeRTOS task. So here we've defined our LED pins. We've attached the red LED to D0, then the green LED to D1. Then since we'll be having two tasks, the first task is to handle the first LED, then the second one is to handle the second LED. So yeah, that's it. So here we have our first task, which is blink LED, LED1. Then just like the normal Arduino code, we say pin mode, we have the pin, and then it's an output. So okay, sorry, yeah, that's it. Then here we have our loop for how the LED will be blinking. So this one is a loop inside the task, but it will not affect the other task. So we'll blink the LED after every 500 milliseconds. Then for period, we are not using delays here. We are using this period. So then we have the second task is to blink the second LED after every 1 second. So here in the void setup is where now we create our task. So here's the first task. We'll name it blink LED1 task. So okay, this is the function that we were having up here. Yes, then this is the name of the task. Then here, this is the size that we are allocating to this specific task. So let's say we're having another task like collecting sensor data, which would be more complicated. We'd assign it a more memory size. Then parameters, you can ignore this since because it's a simple task, we don't need to have many parameters. So for priority, let me show you this. See, higher number is equals to higher priority. So since it's a simple code and we have only 2 tasks, we can just use the same priority for the 2 tasks. So creating the second task is just same as creating the first one. So let's say we wanted to add another LED, we could just create another task down here. But remember, you also have to have a function for it up here. So you'd also create the function up here. So then in the void loop, so nothing happens in the void loop. So since everything is handled by the task, you don't need to do anything in the void loop because the main reason we are shifting to FreeRTOS is because we don't want to have delay. So we'll have nothing in the void loop. So this is just there for the sake of it. So I'll run the simulation. So yeah, as you can see, there's a time when this one is blinking the LED at its own rate, and this one is also blinking at its own rate. So this one is after every second, this one is after every half a second. And you can see that everything is happening at the same time. So with the old method of doing things like running things in the void loop, like for example, the previous one, you saw that this one had to blink faster than this one. So they had to wait for each other. But as you can see, this one is happening, both are blinking at simultaneously. Yeah, that's what I would say. So this is just a simple example, but we'll go to another example now where we are having sensor data collection. So I think we can go to that one. So let me go back to the slides.
Pardon, Nick, before we move to the next, there's a hand up.
Okay.
Bran has raised his hand. So
thank you so far for the session. First of all, it's my first time attending it. I had a question. I was looking at when you're creating the tasks, and you said that like the stack size, the reason as to why the value is that value, like 2048, I wanted you to make it clear, and someone will still ask, what matrix do you use to assign these values? Can I have 300 as the stack size? Can I have 2020 instead of 2048? Or, and at the same time, just repeat what makes me have a larger stack size for a different task and a lower task size, a stack size for another task. And then one last question also, because it's my first time, I wanted to know about this walkway, this interface. Is it free source? Like, do you need to pay for you to use it and do simulations? And what is its capacity? But thank you so far for the session.
Okay, thank you also for asking the question. So yeah, Woku is an open source and it's free. So anybody is able to use it, but it's limited. For example, if you saw me running the other example, there was a time it was asking me to pay for the runtime. So you see, you can be able to do simulations, but it's limited. You can't run simulations, maybe more than 10 simulations at a given time, especially when you are running a complicated simulation. So sometimes you are able to face that challenge, like where it's telling you you don't have more runtime and you have maybe to pay for it. But running the basic simulations is normally free, you can be able to do that. And also when it asks you to, like, maybe you're out of runtime, you can always refresh the end. You'll be able to run the simulations again. So let's go back to the question about creating the task. So you normally use even numbers. So I think if you've been in programming for long, you know that we normally use is it bytes? Yeah, the bytes you normally see there, it should be divisible by 2 because normally 1 byte has 8 bits or, yeah. So for example, we are assigning this stack size in bytes. So we have to make it an even number. That's why we are having this 2048. Then we also normally have the minimum stack size you can assign a specific task. So I believe for this is 2048, but you can go as much as you'd like. And it also depends with the microcontroller you are using. If your microcontroller is more powerful, then you can be able to assign more stack sizes on your tasks. So for example, this blinking LED task, we don't need a lot of stack size. That's why we are using this as a smaller stack size. Then you are asking, how do you know which stack size to allocate to your task? Let's say we were having another task like displaying something on a TFT display. You see, that's a more complicated task because there's a lot of things that are running at the same time. So with that, you'll have to assign more stack size to your task. Another example is, this is another example. Okay, that's the best example I can come up with right now. Or let's say, yeah, you're doing something related with BLE. Let's say you're transmitting data over Bluetooth to another device. Then you'd assign that a more stack size compared to just blinking an LED. So I think I've answered all your questions at this point.
Yes.
So, or is there a question I've not answered?
Nick, I'd like to add on to what you've said on Wokwi. For Wokwi, the limitations are only when you're using the web interface, but there's an API, you can download an extension on VS Code, and there's an API you can use with Platform.io. I don't know if you know the IDE, Platform.io. So when you're using Wokwi on Platform.io, all the limitations, the runtime, etc., they're not there in the Platform.io version. The VS Code extension version. So in our first session of this series, we covered on how to use Wokwi on VS Code. So I'll share the link to that session, or maybe a YouTube tutorial on how you can do that. The limitations are only if you're using the website, but on VS Code there are no limitations. Yeah, you can continue, Nick. I hope, Brian, your questions have been answered.
Yes, thanks.
Yeah, so
Okay.
before I continue, there's something I think I did not mention. Let me go back to it. Yeah, I think I did not talk about task scheduling. So when you're using FreeRTOS, you are able to schedule tasks. Let's say I can be able to schedule like this task happens at this time every day, or maybe happens 10 seconds after this one happens. So you can be able to assign a specific time for a specific task to run. Let's say every day, at maybe 3 times a day, my data will be sent to the cloud. Let's say you have deployed a sensor to the farm and you are collecting a given data. Let's say moisture data. You can be able to assign tasks like after maybe collecting 50 samples is when you can send it to the cloud. So I think maybe I can talk more about task scheduling in the next example. So let's go to it here. This one. So before I continue, could you confirm if you can see my screen?
Yeah, I can see it.
Yeah. So for this example, I'll be showing you how to collect
Pardon,
data
Nick,
from.
there's a hand up. There's a hand up.
Okay.
Ian, you've raised
Yeah,
your hand.
that's. Ian, do you have a question?
Maybe it was accidental. Or if you have a question, you can type or unmute. If there's no question, Nick, you can continue. Maybe it was accidental.
Yeah, so this is a real life example of how you'd apply FreeRTOS. So we have a DHT sensor here, and we are still using the same microcontroller, the Shell ESP32S3. So this example is showing you, let's say you are using this DHT to monitor the temperature and humidity of your house. So like you're supposed to send real-time data to the cloud. Maybe you are monitoring it using a web app or a mobile app. So what happens when you lose internet connection? Let's say you are in the middle of collecting your data, then you lose internet connection. So normally what you normally do when you're building your code for, let's say, something like this using the super loop method, you'd say like every time we lose an internet connection, we'll try to connect, then we send the data. But you see, let's say your internet is completely cut out for the next 2 hours. So you'll see the microcontroller will keep on trying to reconnect to the internet instead of focusing on collecting the data. So let's say something happens where, let's say the temperature rises, for example, there is a fire. You see, you'll not be able to know that, or maybe there was a rapid temperature change. The microcontroller will not capture it because its focus was trying to connect to the internet. Another example would be, yeah, let's say you are logging in the attendance of your employees. Let's say you have an attendance logging device where your employees can maybe scan their fingerprints, then the real-time data of when they do that is sent to the cloud. So let's say you lose internet connection, your device will be focusing on reconnecting to the internet instead of focusing on maybe collecting the timestamps of the clocking in of your employees. So I'll show you how you can bypass that, or you can make your code maybe more efficient to handle such situations. So just like before, we'll have to include the FreeRTOS app here. Then we also have to include the tasks. Then this time we'll be using queuing. So we also have queuing in FreeRTOS where you queue your tasks. Let's say this one happens, then the next one, then the other one. Then since it's we are doing something with internet, we have to include the Wi-Fi. We also have to include the HTTP client. Let's say we are pushing data online via HTTP requests. Then the DHT library for the DHT22. So here's where you define your Wi-Fi credentials. So this is not necessary right now because I'm just showing you a demo, but the links to this will be available on the slides which I'll be sharing, so you can be able to practice with them on your own. So this is an example of a server where you'd be sending your data. So I think I'm sure most of you are already familiar with this, so I won't be talking much about it, but just in case someone does not know about it, so here's where we define our pin. So we have attached our DHT sensor to this pin D2, then our sensor type is DHT22, then yeah, here is where you initialize your DHT. So it's initialized by using the DHT pin and the DHT type. So unlike last time where we had 2 tasks, this time we'll be having 3 tasks. So the first task is to collect data. The second task is to manage the connection with the internet connection. Then the third task is to push the data to the server. So here we have our parameters to store the temperature and the humidity data. Then we have this one to store the timestamp. Since we'd like to know every time we collected the data, let's say we'll need it maybe to know, maybe at noon the temperature was this, maybe 2 hours later the temperature was this. So we need to have the timestamp. So let's continue. Here's where we define our queue, like the one for passing data, sensor data between the tasks. So in FreeRTOS, the tasks are independent. So you need to have a way for your tasks to communicate. Let's say maybe passing data from one task to the other one. That's why we have this. So the maximum stored readings is 100. So let's say we lose internet connection, we'll need to store these readings. Let's say we lose the internet for maybe 30 minutes. Our sensor will keep on collecting the data and storing them on the microcontroller. Then later on, when the internet is back, we can be able to push all this data that we've saved on the device to the server. So because we are storing the data inside the microcontroller, we don't have to store a lot of data because we could have issues with the memory on the microcontroller. But let's say we had an SD card connected to the microcontroller, we'd say maybe we save 1,000 data points. Yeah, so Let's continue. Yeah, here's where we define our first task. This is the data collection task. So it's just basically reading the data from the DHT. Then, so when you're collecting data with sensors, you need to check if the data is valid. Let's say, for example, the sensor is not working. For example, if you use the DHT11, you notice that sometimes you are not able to collect the data and it normally gives you a value like, okay, let me just type it here. Normally gives you a value like this. So we don't have to store this value. So we need to check if the data is valid before we store it or before we send it. So here we try to send the data. Let me zoom out so that you can see it clearly. Yeah, I think that's better. So here we check if we still have space to store the data or we don't have the space, and also if the internet is connected. So let me show you the next task. So here's the task for connecting to, like, the task that manages the internet connection. Let's say if we get disconnected, this is the task that will be responsible for reconnection. So we want to interfere with the other tasks, but rather this task will be running independently, trying to connect to the internet. So then we have our final task, the task to send the data. So you see, this task checks if the Wi-Fi is connected. If the Wi-Fi is connected, we send the data to the server. But let's say the internet is not connected, we store the data locally on the device. So let's continue. I think most of you are familiar with how we initialize Wi-Fi on the ESP32. Just like before, here is where we also have to define the task. So for Brian, who was asking about the memory, the stack size we assign to every task. So you can see from here, compared to the previous one, we've doubled the stack size of the task. This is because these tasks are more complicated compared to the previous one where we are just blinking LEDs. That's why we are assigning more memory. Then you can also check on the priorities. You see this, you have priority 1, this you have priority 2, and this is priority 1. So just like I told you before, the higher the priority number, the more priority that task gets. So we can see that the connection manager, the task to reconnect to the internet, is given a higher priority. So this one always, that means that this one is always run. So the device will always be trying to reconnect to the internet. Then the data center has the same priority as just as the data collection task. Then again, we don't have to run anything on void loop because everything happens on the task manager. So let me run the simulation. But okay, as I run the simulation, nothing specific will happen because you're not sending the data to the cloud. But you'll see okay, you'll see these statements being printed on the serial monitor. So let's try to run the exam. So as this is happening, maybe I can explain something else. So I don't know if some of you are familiar with TinyML. So TinyML is just tiny machine learning. So this is where you run machine learning model on microcontrollers like this one. So this one, okay, since the simulation cannot run, maybe we can refresh this. So yeah, let me continue talking about TinyML. Let's say we are doing...
Your voice is Nick. Nick, can you hear me?
Yeah, I can hear you.
Can you hear? Your voice was kind of breaking, and I think your screen has froze, or I'm not sure. But on my side, your screen has froze.
So I don't know. Can other Ryan, can you confirm if your screen is also frozen or you can see my screen clearly?
I can see you scrolling up and down. I don't know if you're doing it now that way.
Yeah, I'm doing that right now. So maybe Collins, the
Right now
problem
it's,
is on your
it's
side.
better now. It's better now. It's
Oh,
better now.
okay.
Yeah,
Okay,
sure.
thank you for clarifying that. So yeah, I was talking about TinyML. So TinyML is just like the other machine learning, but so with this, you are deploying the machine learning model on a small device like this. So this is the Xiao ESP32S3 Sense. So this one is a photo you normally attach the camera and the microphone. So an example I'd like to give now is maybe we are doing keyword spotting. So keyword spotting is you're trying to identify a specific keyword from speech. So let's say I've created a specific machine learning model that's supposed to identify the word fire. Then we've deployed it in a school. So when somebody shouts the word fire, the microcontroller or the model running on the microcontroller is able to identify that specific keyword, then maybe start the fire alarm, or maybe, yeah, let's say start the fire alarm. So the reason why we use FreeRTOS when doing such tasks is the microcontroller has to always listen for what's happening. So I think I'll change an example because that was not convenient. Let's say we are doing a machine learning model to detect the keywords. Let's say we have our robot. We are supposed to tell it to go, come back, turn left, turn right. So the microcontroller needs to always listen for the keywords. Let's say the first the first thing I said was go. So the robot will be moving forward. But maybe I say left. So the robot also needs to turn left. But let's say we're using the old method where we are running everything in a loop. So maybe the microcontroller was first listening, then I say go. So it will be running the go task. So the robot will be moving forward. But when I say left, maybe the robot will not listen because it's currently handling another task. But with FreeRTOS, you can have a specific task to always be listening for the keywords. Then another task could be dealing with the actuation. So I could say go, turn left, turn right, and the robot can respond in real time because everything is handled independently. I don't have to wait for the robot to go forward maybe for a few seconds, then it waits again to listen to another command. Yeah, that's an example of such an application. So all the links to this will be available, and you can get access to them and try to do the some simulations on your own. So summary and some takeaways you can maybe something you've learned from this session. So FreeRTOS enables multitasking without blocking other processes. So this is what I've been explaining from the beginning, so you already understand that. Then the thing about work we talked about it. So this presentation mostly was a reference to this FreeRTOS for Beginners by Sean Hemel, and a tutorial I myself did. You can check it out. So these are clickable links. You can check them out. So maybe I could give you an overview of this one. Can you see my screen?
Yes, you can see it.
Yeah. Make sure you guys go through this tutorial because it's explaining a lot of things. So it's talking about the general purpose operating system and the difference with it and the real-time operating system, the super loop, the RTOS, what it does, and also you can see it has a lot of parts. There's part 2, part 3, part 4, part 5. You can go check out all of this. So because I was in a hurry, I was brushing through everything. You can go through it in detail.
Nick, pardon, can you like share the link on the chat kindly?
Yeah, I'll share the link. So the link is on the slides, and I'll share the slides, but maybe I could also share the link on the chat. Then,
Okay, cool.
yeah, and then this is a specific, let me click on this. Yeah, this will be explaining the examples I was showing you. So you can go check this one out. It's like running FreeRTOS on the Shell ESP32S3. So here you get to learn more about FreeRTOS. So maybe there's something you did not catch maybe when I was talking. You can go check it here and you'll be able to find it. So let me try to wind up. So any questions before I continue? If you have a question, just unmute and ask your question. So seems there's no question.
Okay, I have a question.
Okay.
Unanisikia?
Yeah, I can hear you.
I was asking, let's say I've seen you've created a task A. Can task A communicate to task B?
Yeah, that can happen. So maybe I can show you. Yeah, this is the example I'll be referring to. So here, this is a queue we are creating for passing sensor data between tasks. So you can be able to communicate from one task to another. Let's say you need data from task 1 to pass it to task 3. So you can be able to do that. So go through this example and the link I'll be sharing so that you can be able to learn more. Let me just share the link immediately before I forget.
As Nick shares his link,
Okay, I cannot
these are
access the chat.
okay. You can
Yeah.
send the link to me in my WhatsApp, then I can share it. That's strange, but yeah. I've also
Yeah.
shared the link to our
So
WhatsApp group. That's where the slides will be shared. Okay, take it over, Nick. I'll communicate at the end.
okay, no problem. So I told you I normally contribute to a lot of open source projects and I also build some of my projects. So this is my Hackster.io account. You can go check it out. Just go to Hackster.io and search for my name or my username. So here are some of the projects. There are a lot, and I want to be able to go through each one of them individually, but you can just go check them out. They are mostly related to IoT, TinyML, and robotics. Yeah. So this one is the most recent one, and it's one of my favorites. So I created this tiny robot. I think most of you saw it. So yeah, that's it. So I advise you guys to always document your projects. And Hackster.io is a free platform where you can document them for free, and a lot of people can be able to access your project. So always do that. You never know what happens when you do that, because you get a lot of exposure. For example, you can see this project has 1,000 views. So if you just work on a project, don't keep it to yourself. Go share it out there. You don't know who will come up and maybe offer to help you with the project, or maybe contribute and help your project be better. Yeah, I think I just wind up there. So let me stop this. So I'll be sharing these slides to Collins, then he'll share it to you guys. So yeah, you can follow me on my socials. These applicable links, you can go find me anywhere on these platforms. And in case you have any questions regarding what I just presented today or regarding other projects, feel free to reach me through these platforms. I'm always active and I normally post projects weekly. So yeah, thank you. Collins, you can
There you
take
have it.
over.
Let's give a round of applause to Nick. Let's give a round of applause to Nick. That has been a very informative session. Even me, I've learned a lot. I've not really interacted with the FreeRTOS, so for me, it was a learning session, co-hosting, stroke learning. Yeah, so okay, Nick will share the slides to me. So I'll share this. I've shared a group to WhatsApp, a link to WhatsApp on the chat. So kindly join that group. That's why we'll be sharing the slides, the recordings, and information on the next session. So this series usually happens every Monday, 8 to 9. So next week, same time, same place, we'll be having another session. I'll communicate on that in a group. So make sure you join the group. Another thing I'd like to
Not see
appreciate
that.
Nick. Yeah, so I called up to him to have this session, and Nick is a big busy guy, but he tried to make time to have this session to share the knowledge with us. And let's give him a round of applause again, because I believe you've learned a thing or two or three from him. Yeah. So apart from that, I think we can conclude there. From my end, I don't have much to say. Just to wish you a great week, a good week of building. We'll also share the links. You can look into more into FreeRTOS and maybe work on a project. If you build something cool, you can come forward and maybe you can give you a chance to showcase what you've worked on. Yeah, these are also, we also have show and tell. So if you have something cool you've worked on, you'll also get a chance to share. So yeah, I guess we can call it a night, and I wish you a great time and a fantastic week. Looking forward to see you next week, same time, same place, but a different link. Yeah.
The
So
link,
yeah. Okay.
sorry.
Pardon,
I have not seen the link. I don't know. I can't see
Brian,
the
you're saying
chat or
something?
something. I'm saying that the chat on my end is
Oh, I've
disabled,
said
so I can't see.
wow. That's I don't know how we can go about. Okay.
I also
How can we?
can't access the
Let me
chat,
just
so
like say my number, then you can. How can we go about that? Maybe I can like say out my number, then you can like text me on WhatsApp, then I'll add you to the group and also share the information to you. So my WhatsApp number is 0736 257 293. 0736 257 293. Just text me on WhatsApp. If you can't access the chat, text me. I'll share the resources to you. For those who can access the chat, kindly join the group. The number is 0736 257 293. That's my WhatsApp number. For those who can't access the chat, just DM me. I'll share the resources to you. Yeah. Is there any other issue or? Okay. Let me stop the recording. You're free to leave. Our session has ended. Looking forward to see you next week, same time.